All right, welcome back as we start talking about convection mass transfer. So, this is very basic convection principles. We're not going to get into the weeds, and this is just to give you a little bit more context as an electrochemist. So, the first thing that we assume is that as a fluid is moving over a surface, right at the surface, there's no fluid velocity. This is called the no-slip condition. And you can see that as you move upwards, we have depressed fluid velocities. And then once we get out to where our fluid velocity isn't being depressed anymore because of the no-slip condition, that's when we say we've left the boundary layer. So this is the convective boundary layer. The next thing to note is that a really common, application of convection principles is the rotating electrode. So in this case, you take a cylindrical piece of insulating material, you put an electrode flush to the bottom of it, and then you spin this cylinder. And this is a rotating disc electrode. It's the most common form of a rotating electrode. And based on how fast you spin it, you can control the diffusion layer thickness. So if you go through and you do the math, you can come up with the equation for the limiting current. And here you have the number of electrons exchanged, Faraday's constant area, diffusivity. You have the frequency that you're spinning at, you have the viscosity, and you have your concentrations. And so if we look at the general form for the limiting current, then in this case, we have a mass transfer coefficient. And so what you can actually do is you can combine these two equations into this one. And here we have talked about how the mass transfer coefficient is defined in electrochemistry as the diffusivity or the diffusion coefficient over the diffusion layer thickness. So we can get an equation for that. And then because we have diffusivity on both sides of the equation here, we can actually solve for the diffusion layer thickness based off of the diffusivity and how fast you're spinning things, and the viscosity of your solution. So these are really handy equations. This is the Kentucky-Lovich equation is what this is referred to as. So let's talk about some other ways that we can have, let me just mute that. Some other ways that we can have bubble-driven flow. Or convection. So if we're making bubbles, then the fluid will rise up with the bubbles, and this will cause convection. Likewise, if we're plating out a heavy metal, then the solution that we're depleting of these heavy metal ions becomes lighter, and so it will also flow up. Here, this is a nice little video by Jason Dugway showing how these bubbles induces convection in this tank. And you can see that, there's, of course, randomness. It's convection. Convection is random. But there's a general circular motion going on in the convection here. And we would expect a very similar thing to occur in our electrochemical experiments if we're producing bubbles. So there's a very interesting paper that's come out recently on natural convection in molten salts. So molten salts, these are experiments done in furnaces, and so there's actually thermal gradients, density gradients because of that, and it leads to some mass transfer coefficients on the order of a micrometer per second, which is equivalent to a one rotation per minute rotation with a rotating disc electrode. So, it's not incredibly significant, but when you're operating at low scan rates, for instance, this these voltammograms are 2 millivolts per second, then it can actually start to play a role. And of course, if you have things like you're making bubbles or you're plating out metals, then that can augment the natural convection, and you can start having density gradient, more significant density gradient convection as well. So something to look out for. So the question for this video is, when should you consider convection as being significant? So go ahead and write down as many, of the answers as you can, and then in a few seconds I'll give my solution. All right, so I would say that you should consider convection being significant in the following conditions. So if you're measuring with long time scales, this just gives convection more and more of a chance to play a role in your experiment as your diffusion layer thickness grows. Also, if you're producing bubbles, if you're plating out metals, you should expect there's going to be some density, some convection effects. If you're stirring, flowing, rotating, of course, or if there's a decent thermal gradient that could lead to a density gradient. So that concludes the video on convection, and hope you'll join us next as we talk about migration. Migration will be the final video in the mass transfer lesson.